A projection operator is a linear operator that maps a vector onto a subspace by projecting it onto that subspace. This means that the projection operator takes a vector and projects it onto a subspace, which results in a new vector that lies within that subspace. Some examples of the use of projection operators in various fields include: in computer graphics, projection operators are used to render three-dimensional objects onto a two-dimensional surface, such as a computer screen. In physics, projection operators are used to study the properties of quantum states. In engineering, projection operators are used in control theory to design feedback systems that stabilize unstable systems. To project a vector onto a specific direction, we can use the outer product of the unit vector as a definition of the projection operator. The projection operator has three important properties. First, the square of the projection operator is equal to itself. Second, the projection operators are mutually orthogonal, which means they form a matrix of all zeros. Third, the sum of all projection operators equals the identity matrix, which is also known as the completeness equation. According to the geometric interpretation of the inner product of vectors, the inner product of vectors ek and v is equal to the length of the projection of vector v onto vector ek, denoted as ck, multiplied by the length of vector ek. Since the length of vector ek is 1, it follows that the inner product of the vectors is equal to ck. In other words, pk times ket v represents the projection of vector v onto vector ek. This means that pk times ket v gives us the length of the projection of vector v onto vector ek. Assuming A is a normal matrix with eigenvalues and corresponding eigenvectors, then A can be represented in spectral decomposition form with its eigenvalues and eigenvectors. Since A is a normal matrix with a set of orthonormal eigenvectors, it can be easily proven that the formula holds true by using the completeness equation. When A acts on any vector, its geometric interpretation is as follows: the vector is projected onto each of A's eigenvectors, and then linearly combined with the corresponding eigenvalues as coefficients. Let's consider an example. First, we use the H-gate to generate two standard orthogonal bases. The projection operator for each orthogonal basis is given by their outer product. Using matrix operation rules, we can obtain the corresponding matrices for the projection operators. According to the completeness equation, the sum of all projection operators is equal to the identity matrix. Since the projection operators are mutually orthogonal, the product of any two projection operators results in a zero matrix.